that before the first lecture will be about the generation for reactor types. Now I'm calling for Mate Siebert. Is here with us to speak about this very interesting topic. So Mate, when you're ready, you can start sharing your screen in your presentation.
Okay, thank you very much. Good afternoon to everyone. And yeah, I found this screen. Okay, so do you see my screen now? Thank you very much.
Yes, perfectly.
So today's presentations will be somewhat related to my presentation yesterday. Now I will, speak about something like the actual development directions in nuclear. What kind of new reactor types are envisioned on the medium term, let's say. First of all, let's talk a little bit what are these generations of reactors and why it is the fourth. What is this Generation 4 International Forum, and what are the main goals set and how to achieve them. So these are kind of general approach to Generation 4. Then I have many slides about Generation 4 reactor types, but due to the time limitations, I will not be able to really go through, only to show you some spotlights, some interesting features. And the presentation is shared with you through the drive, so you can go through it yourself. I hope you will find some interesting information in it. So concerning Generation 4 reactors, maybe many of you have seen something similar than this graph. You can see here that we group the reactors according to their age, their year of commissioning into 4 generations or 5. We'll see if we consider. So there were the early prototypes which started up in the 50s, and some of them operated even till the millennia, but nowadays they are practically all shut down. They are very diverse in technology. Practically all of them were prototypes or first of a kind reactor. Then there is a very successful generation, the Generation 2, which are the first standardized large-scale industrial, real commercial power stations. So they could see a huge development of nuclears from the 70s, and many of them are still operating at our lifetime, under lifetime extension, preparing for long time operation, which is one of the current challenges of nuclear, that we have to keep these Generation 2 reactors in operation with increased safety levels. And then came the Generation 3, which is a result of some evolutionary changes. So some gradual changes from Generation 2, and such reactors, the commissioning of such reactors started around the year 2000, and some of them which are commissioned like from 2010 or afterwards are even called Generation 3 plus, because there were some further development, some of them especially due to the lessons learned from the Fukushima accident, and so on. And at that time, the Generation 4 was already dedicated to the so-called revolutionary design. So if we call these evolutionary, then we can call Generation 4 revolutionary, which are based on usually completely different principles than the light water, mainly light water reactors of Generation 2 and 3. And this was assumed to be at that time around 2000 when this concept was born, Generation 4, that these reactors will arrive after 2003, so that they will rule the new build after 2003. So these are summarized on this slide, and I also wanted to show you how the nuclear generating capacity installed developed through these generations of reactors. So this is what you can see. The generation 2 is in fact a very successful generation with an immense increase in nuclear generating capacity through the 70s and the 80s. And then things slowed down for various reasons, and generation 3 tried to have a reply, provide a reply on that. But obviously it's still not brought some nuclear renaissance. So generation 3 plus includes some more innovations, both in safety and in economic, and in order to be able to build reactors faster and so on. So this is to say that many of the reactors operating today are still belong to the generation 2, but what we construct today, those usually belong to generation 3 plus. So now go to generation 4. This whole idea comes from this generation 4 international forum, which was an initiative from the United States in 2000. And it practically provides a legal framework for this very complicated development process, which could lead to the new reactor types, because it's quite obvious that it will need international cooperation between countries in order to be successful. The most important things that this Generation 4 International Forum issued a roadmap which defined certain goals. We will go through these goals, and selected 6 nuclear systems which are in the focus of the development. So first, let's see these 6 systems. It's quite a famous list nowadays. It's quite inclusive, so practically all possible technologies are given here. You can see that 3 of them are specifically fast reactor with different coolant, sodium, lead, and gas, while the others are mainly rather thermal or epithermal reactors with focusing on very high temperature, or the use of supercritical pressure water, or this is a really exotic design, the molten salt reactor, where the fuel itself is in a liquid form. So why to do these reactors? What are these goals which we would like to fulfill? First, sustainability. You will see I put here some comments whether this goal is really needs an innovative technology. And as we could see yesterday in the nuclear fuel cycle presentation, in order to improve the fuel utilization efficiency, so the recycling of the used fuel, or to minimize the nuclear waste, so to recycle also minor actinides. There we need innovative technology, practically fast reactor technology. We will see that the energy conversion efficiency, which needs that we need to move to a higher temperature, also needs some innovative technology, usually gas cooling or something similar. And it's also which we see that new energy products, so besides electricity, that also needs innovation. Obviously, safety and reliability is also a very important goal, but it's like a little bit controversial that here what is best for safety is a proven, well-known technology. So here I would formulate it in a way that we need to do all these innovations without interfering with this high level of safety, which is already achieved in the generation 3 and 3 plus. So like when we say that there is a very low likelihood of degree of reactor core damage, this is practically that we would like to keep the generation 3 plus, so the conventional, the evolutionary design goal. And also that to eliminate the need for off-site emergency response, that means that we need severe accident management, so the mitigation of the consequences of a potential severe accident. Then there are two more goals. The economics, this again needs some innovation because this is not the strongest part of or side of nuclear energy nowadays. That the goal is to have a life cycle cost advantage over other energy sources and have a level of financial risk comparable to other energy projects. And that would need obviously nowadays smaller units and or even load following in the operation. And then the last goal is proliferation resistance and physical protection, so that these reactors should be very unattractive for diversion or theft of weapon usable materials, and to provide an increased physical protection against acts of terrorism. Again, here the best is the proven technology and the one-through cycle, the open cycle. While when we speak about the sustainability goal, there we would need a closed fuel cycle. So the harmonization of these goals is a big challenge in these generation 4 reactor types business. Now let's have a look into the what is the progress of the development of these reactor type. It's a good analysis can be given if you look at the original roadmap from 2002, which give some deadlines for the demonstration of the viability and the demonstration of the performance of these reactor types. So this would be actually a date to at least an experimental reactor or a prototype to operate. And if you look into the update of this roadmap in 2014, you can see that there are reactor types where which did not have much progress, and there are reactor types which could show really progress in this in that decade. So, like you can see that for the molten salt reactor and the gas-cooled fast reactor, these deadlines are like extended to like 2030, and even the viability is to come, while the other 4 reactor types, it was considered that the viability is proven, and even the performance demonstration can be expected in like a decade. So let's look into a little bit more into these goals, so that in the sustainability goal that generate energy sustainably and promote long-term availability of nuclear fuel, we've discussed yesterday that the identified uranium resources are sufficient for about like 135 years at the present consumption rate. Also, we can see that the mining has the largest environmental impact among the processes of the nuclear fuel cycle, and the uranium which is mined is utilized only with a very small efficiency. And we could see that fast reactors may help in this extent. This is why in the generation 4 reactors there is so much focus on fast reactors. In the other sustainability goal, it was said that to minimize the nuclear waste and reduce the long-term stewardship burden, we could see again yesterday the partitioning and transmutation technology, which again needs fast reactors, since minor actinides are all fissionable in the high energy neutron spectrum of fast reactors. So this is again some goal which promotes the use of fast reactors among the generation 4 types. If we look into the economics, then on one side, the efficiency needs to be increased. So with that, we can have higher output, electricity output from the same size. And that our problem is that the complex systems like nuclear power plants needs to grow very large to provide a competitive unit cost. And this is why our reactors in the present are so large unit. But this large unit size imposes obviously large investment and a large level of financial risk. So one potential advantage of small modular reactor, despite that the economics of scale would suggest to build as big size as possible, that they may reduce the financial risks in some extent. Then if the production can move away from pure electricity production to other production goals, like production of hydrogen. Hydrogen economy can be a very important factor in like the net zero goals in climate change, or the process heat, to provide heat for industrial processes directly, or heat storage, which is a form of energy storage and very important in integration of intermittent renewable sources into the electricity grid together with nuclear. Those can help also the competitiveness of nuclear production. Some inherent safety features also help in the simplifications and make smaller size. This is like why lead-cooled fast reactors are an attractive idea for small modular reactors, because you can very much rely on natural circulation when your coolant is lead. Concerning the energy conversion efficiency, you may notice that the theoretical maximum of efficiency can be given by this formula. So this means that this temperature step from the cold temperatures to the hot part of the cycle has to be as large as possible. This practically means that you need to increase the hot part, so increase the temperatures in your cycle, in your energy conversion cycle. This is limited in when you have water as coolant, which is a very nice and very available and very practical coolant, but it has a problem with the critical heat flux. So when your heat flux increases, you start to give more and more heat to the water. You know that it starts boiling, then it starts developed nucleate boiling, so with many bubbles. But at a certain point, it starts to a transition to film boiling, which means that the steam layer will divide your surface, so wall, the cladding wall from the coolant, and there the heat flux and the heat transfer drops a lot, and there you have in light water reactors a risk of fuel failure. So this limits the temperatures in water cooling. Also in water steam systems, so with the Rankine cycle, the phase change limits again the efficiency. So the solution can be like supercritical pressure water. So when you on the phase diagram of water, you go above this supercritical pressure, then you may then you practically get rid of a phase change. The phase change is much more smoother. The other can be like the gas coolant, or at least as a secondary coolant, which allows you to use the Brayton cycle, so the gas turbine, and the combined cycle. So both use the gas turbine and then still go to a steam generator and use a steam turbine. The liquid metal and molten salt also gives very high possibility of reaching very high temperatures. Here the problem is obviously with the risk of freezing at low temperatures. Concerning the process heat applications, many industrial processes can be fed with temperatures which are above the potential temperatures which you can obtain from the conventional light water reactors. These are all for the high temperature reactors. Again, a good efficient production of hydrogen needs very high temperatures. But the generation of steam, which can be used then in like a neighboring factory for as process heat, also needs higher temperatures. The application of light water reactors that practically goes down to district heating and seawater desalination. And then other potential in high temperatures is energy storage. So that in a high temperature reactor, you may realize an energy conversion cycle in a way that you have the option to direct a part of the heat produced in the core, not to the this first generator, but into an energy storage, a heat storage system to heat up molten salt, in this case, from a low temperature tank and pump into the high temperature tank by heating up. And then you can store it here and use another energy conversion cycle to use the heat stored here whenever you wish to produce energy. It means that without modifying the nuclear power in the core, your reactor system, complete power plant, can be very flexible and load follower. Obviously, on the long term, as average, it will not be able to produce more power than what is the maximum power of the core. But you can direct some of the power during low consumption hours into energy storage, and during peak hours you can generate electricity from the stored energy. Again, in order to make it efficient, you need high temperatures. You can see here the temperature 680 and 280. You need a high temperature for efficient energy storage. Okay, and let's look into safety and reliability only very quickly. The most important thing is that the design should be like what is called design by safety. So the design features are not built, are not added onto the reactor design, but it is built in, which means that throughout the complete design procedure, the safety has to be there. Which means that in this generation 4 International Forum, a new methodology, which is called the Integrated Safety Assessment Methodology, has been developed. And the big novelty of this is that it starts already in the phase of the preconceptual design. In the preconceptual design, you cannot do quantitative, detailed, like licensing safety analysis, but you can start some kind of qualitative processes and phenomenological identification of different safety problems, which then through the complex conceptual design, as you reach the final design, will evolve into a complete probabilistic and deterministic safety analysis, which is required for the licensing and operation of the reactor. So this new approach supposed to be guarantee that these reactor types will also excel in safety and reliability. As a quick overview table, so what is the role? As you could see, there are 3 fast reactors, which can be either fast breeder or transuranium burner, so for transportation purposes. And the others are rather for thermal designs. And you can here see also the temperature, so like the gas-cooled fast reactor, the molten salt reactor, and what we call the very high temperature reactor, which is a thermal reactor, are especially designed for very high temperatures, but even in the others, you have higher temperatures than in our conventional reactors. A little bit about fast reactors. Why are they fast? Again, you need to remove the hydrogen, so the low mass element, as a moderator. You cannot use water as a coolant because that moderates the neutrons. Because when a neutron collides with a hydrogen, it can ideally pass its complete energy to the hydrogen, while, very simply saying, from a larger nucleus, it bounces back and keeps its energy. You can see here, sorry for the Hungarian titles, but the blue is the fast reactor spectrum, and the red is the thermal reactor, and you will see this huge low energy thermal part, which is due to the moderation, and that this part is practically missing from a typical fast reactor. So these are why the possible coolants are molten liquid metals or gas, which is although light element, but so low density that there will be no moderation effect. I think I will stop here and rather look into your questions and answer rather that, and the other details from the presentation about the to the given reactor types. Maybe you can look into that later yourself. Hopefully you will find some interesting information there. Sorry, so let's say, yeah, Marianne.
Yeah, some question for you.
Yeah.
From Marianne. The first one is, will generation 2 reactor be stopped or revamping is considered to extend their life? And the second one, Marianne asked about the average cost of 1,000 megawatt nuclear power plant.
Sorry, I don't have a figure for the second one right now in my head, and I don't want to say any inaccurate, so I will look into it and give you some number later. The lifetime extension of generation 2 reactors is extending and extending, so there are already consideration of extending the lifetime of reactors which already had one lifetime extension, but it will be for safety reasons it should stop somewhere for sure. And I think we are reaching the limits. I've just got the information that, like, the Nuclear Regulatory Commission of the US decided against 40 years lifetime extension, so that that cannot be such long lifetime extension at once. You have to proceed in smaller steps when you can really ensure that nuclear safety principles are not violated when you extend the lifetime of an older reactor. This is a big, I would say, well, because economically it is very attractive. You already have the reactor, and you do not need many investment, and you have the reactor for many more years. But after a while, it really raises serious nuclear safety concerns. So yeah, there must be a limit for the lifetime extension. concerning the generation 4, yeah, another question.
Yeah.
Are there a generation 4 design which is superior regarded as superior by the community? I think yes. I would say that like sodium cooled fast reactors do operate today, so they are quite proven, feasible design. There are a huge, really big advancement with lead cooled fast reactors, and I think this is really superior for the gas cooled fast reactor, which is rather in the demonstration phase. So there are much more research is needed for the gas cooled fast reactors. Then the very high temperature reactor is also very advanced, but like the supercritical water and the molten salt reactor are much more behind in the development. So I would say the very high temperature and the sodium cooled, which practically exist today, maybe not on that level as generation 4 expects it, but exist, and lead cooled fast reactor, which are almost here. The others are very much in the development phase.
There is one more question from Adolfo. He asked about the 4th generation nuclear power plant is preparing the best technology of storage radioactive waste.
Well, I do not clearly understand the question, yes. But
Adolfo, yeah, you can speak out if you want and reformulate the question.
Okay.
Yeah.
Teacher Meta, good afternoon.
Good afternoon.
Yeah, I can see. I can know that the nuclear power plant is preparing the new technology of storage residual waste.
Well, the nuclear power plant, I mean, the waste is stored, that's a different facility. It's not related directly to the nuclear power plant. But concerns in this respect, the nuclear power plant is that in generation 4 reactor, it is a goal to minimize the amount of the waste to be disposed after. But the reactor development is independent from actually the waste disposal options or facilities.
Okay. Okay.
Okay.
Thanks so much.
Thank you much.
Thanks so much. Yeah, okay.
Thank you. We are running a bit out of time. Maybe, Mate, if you can write in the chat and answer the question of Ivan.
It's short no, as far as I know, the answer of the last question. Very short.
Okay. So, and in the meanwhile, we can go on and move to the second lecture. Now, there's time for Gonzalo Jimenez giving his presentation about how the nuclear reactors in the future will look like. So, Gonzalo, when you're ready, you can also start sharing your presentation, and then the floor is yours.
Okay, thank you very much. Can you see it clearly?
Yes. Yes, perfect.
Well, the first thing is I have to thank you very much, the previous presenter, Mate, because you simplify a lot my life, talking so deeply about generation 4. So I will try to be as complementary as I can with this lecture. So the idea is not to detail the generation 3 or generation 4 or small modular reactor designs indeed. It's just to analyze which advances has been produced in the nuclear energy regarding those generation that can configure or can be the elements for the reactors in the future. So we will go, let's see, category by category, having a look at the advances that we have experienced in the last years and in the designs that are going to be the future. So just to add one category to the Matthew's wonderful picture is I put myself this modular reactors category in the, let's say, between generation 3 designs and generation 4, because they are enough different from generation 3 to have their own category, and I'm sure they will be the near future will be the bridge between the two generations. So that's the only difference that I want to point out. Well, the first thing is what is the global situation of the nuclear power around the world. So it was 2 days or 3 days ago when I did that. So the first thing is we have 444 operational reactors around, and at the same time we have 51 reactors which are under construction. So it means that the first message is, well, the nuclear energy is, let's say, alive in the sense that many countries are building. It is true that it depends very much on the, let's say, situation of each countries. It's not the same the scenario we have in Europe or the scenario we are experiencing in Asia, which are building a lot of reactors, as you can see, China, Korea, India, and so on. So, of course, there are big differences between regions, but the global message can be there's a lot of attention paid in the construction of new reactors. And not only we have 51 reactors under construction, but we have also a lot of new planning for new constructions in different countries. So that's the picture. There's a lot of reactors on operation, but also we have a lot of constructions around the world. So that's the situation we have. The first thing that, just to give you some fundamentals, is the most popular reactor that has been built in the generation 2 that Mate mentions is the pressurized water reactor, which functions like this. You have a primary circuit in which you have the nuclear fuel, and this is a circuit very high pressure, 155 bars, and it heats up a secondary circuit in which you create the steam, and the steam goes to the turbine, and it creates electricity in the generator, and then it's condensed in the condenser, and so on. So you have this secondary circuit, which is refrigerated, but this tertiary system can be whatever you need it or you have in your place. So two very important things, because we are going to talk about nuclear safety, is the first one is one important aspect is if you have a nuclear operation, of course you need a lot of cooling, but even in the case in which you stop the nuclear fission, you still have a lot of heat, residual heat that you have to cool down. So you will need even a lot of safety systems to help you to do that. Even as I told you, you have stopped the nuclear fission, so you are just experiencing the residual heat. So when we're talking about safety systems that which let's say the primary focus on the cooling, it will cause of the consequence of having this high residual heat in the core, even if we don't have nuclear fission. So that's something that you have to know. Okay, so let's go. So how the nuclear reactors with in the future will look like? That's the thing we were trying to guess. My goal in this presentation is give you some pieces for the puzzle. So I will talk about three main pieces. One will be as nuclear safety, as can be in other way. We will talk about nuclear fuel, and finally we'll talk about strategical aspects such as construction. And with all these pieces, we'll try to build a reactor of the future. So we will go place by place. So the first thing is we will talk about nuclear safety. So in this first category, we'll talk about reactor cooling. As I told you, even if we have stopped the nuclear fission, we will have high residual heat. So we need to cool down the core continuously in the middle of a transient. So for example, if we have an accident, which is, let's say, the most popular one, in which we have a break in the primary circuit and we are losing the coolant, we will need a safety system to compensate this loss and to enter cool and borated water in the primary circuit. I'm talking about PWRs for simplicity. Okay, so in detail, the safety injection system is based on 3 subsystems. Well, the first one is called high pressure safety injection system, which is a high pressure pump that takes water from the residual this tank that is outside the containment. Is a refueling water storage tank. And we have also a low pressure safety injection system, which is taking also water from this place. When this tank is getting empty, then they take water from the sun. That's the thing. So these 2 systems are active. It means that they need alternating current to work. And we have a supporting system, which is the accumulator, which is totally passive. It means that it doesn't need any electricity source to work. It's just only by difference of pressure. So it is a tank, some tanks, depending on the model, that are pressurized at 45 more or less bars. So they enter when the pressure is lower in the primary circuit. So that's more or less how it works. Okay, but what happens if we lost the electricity? What is the situation then? If we have in the middle of this accident and we lose it, we have a chance to survive because we have this diesel generators, and that was the situation before Fukushima. But in case we lose that, we have, after Fukushima, what is called some post-Fukushima strategies. So these kind of strategies are common for the few reactors that are still left from generation 1, generation 2, and those reactors are actually being built in generation 3. So that's how we saw. Okay, how the generation 3 is facing this cooling in other ways. One example is the AP1000 generation 3 plus reactor, in which we just take out the pumps we were naming in the previous slide and get replaced by different tanks. So let's go in detail. If you remember, we have this high pressure injection system ready to inject at high pressures. That's why it's named. It's replaced by a tank, a pair of tanks, one per loop, called core makeup tanks, which are injecting at high pressure because they are pressurized and they have the same pressure as the primary circuit, but they are in a higher elevation, so they can enter whatever it happens. They don't need anything to work. It's just the gravity. We have also the accumulators, like in the previous designs, generation 2. And we have also the tank, which was outside in the generation 2 reactor. We have it inside in the containment. And it's located in such a way that's in a higher elevation to the vessel, so it can work also passively without anything else more than open a valve and inject when the pressure of the vessel is low enough. So as you can see, we have replaced active system that depends on the electricity by passive system that depends only on gravity and the opening of certain valves that can be operated with batteries. So you don't need any electricity source, alternating current available. So that's the fan thing. So this is how generation 3 reactor do it. If we go to the boiling water reactors, then we have a similar approach in the economic simplified boiling water reactor of General Electric, in which we have different suppression and different tanks in the containment building that can provide water directly to the vessel, as in the GDCS pool you have here. We have also pools that can cool down the steam that is being released in the containment, like this PCC pool that you can see upstairs. And we have also systems that can just condense the steam we are producing in the vessel and come back to the vessel in let's say in form of water. So we have all this passive system, doesn't need any electricity more than opening valves, and it can be done with let's say passive valve such an explosive valve, or also like a battery operated valves. So that's the way we are replacing the pumps based on electricity current. This the same, but let's say in a modular way. Yes, all the things we have seen, or most of the elements we have seen, is compressed in this such as compact design. So that's, let's say, the interpretation of this reactor in a modular, smaller way. Okay, we are also talking about different alternatives here. For example, instead of getting replaced in the injection system to the primary circuit, is a replacement of how we can cool the secondary system. So in this way, this Viver reactor from Russia, what they are doing is locating some heat exchangers in the outside part of the containment, which can condense the steam that is produced in the steam generator and come back to them as water. So let's say it's an infinite cycle if you need it. So that's very good for nuclear safety, because it assures you as a heat sink for a very long time. If we are going to small modular reactor, how we can deal with that? That's an example of NuScale, is in which the reactor is in a pool, indeed. So we have the vessel, covering the vessel we have, which is called the containment, and then everything is inside the pool. So in case of a loss of coolant accident or any other cooling transient, we will have different in heat exchanger here that can help us to cool down the reactor. And also we will be inside a pool that can cool for a very long time the reactor, and without the need of any active pump working. And talking about generation 4, we have, let's say, a more advanced approach even, that is that one in which we have a fuel that is designed to be cooled basically by radiation and convection with air, without having any special system to do. It means that in this reactor of very high temperature, in case we have a loss of coolant, we don't have to do anything special, but just stop the nuclear fission. So the residual heat is being transferred by radiation and convection to the exterior part of the reactor primer circuit, and directly to the building, which is being made with the natural circulation systems to avoid any action of any pump or any active system. So that's advanced approach to that. The same can be said to the U battery reactor SMR. It was a design proposal design. And a different approach is the Westinghouse Da Vinci one, in which they have this solid core with heat pipes that can just directly heat the core in operation, and let's say with the shutdown, without a fluid circuit itself. It just heat pipes like you have in your microchips in your PC, but bigger, of course. And with a very good advantage is such a compact that you can see the reactor can be transported even in a truck. So that have a lot of advantage in that sense. Okay, if we talk about the containment, if we have a break in the primary circuit, all this mass and energy will be released to the containment. So we have to avoid any rupture of the integrity of the containment and release of potential radionuclides to the exterior part of the environment. So we will need different systems. For a generation 2 reactor, we have this spray system, which is an active system that operates in case the pressure and the temperature of the containment is big enough. How it's, let's say, an alternative of that for generation 3 is we have, for example, for AP1000, a containment that is designed to be as a heat exchanger. It means that the air is going inside and being is cooling the containment of the reactor during operation in case we need more than that, because it could be not enough in an accident. We have this big tank here that can discharge water, let's say, around the metallic layer, and then we will have also this cooling by water in the outside. Everything is done without any pump, any active system, so only opening valves if needed. In the case that we have seen in the in the simplified boiling water reactor, we have also this this concept. As I told you, the steam we have released in the containment is being cooled in this PCC pool, and getting directly to the gravity-driven cooling system that can put water inside the vessel if needed. In the NuScale SMR, we have a design such as having it inside the pool. It is enough cooling with this pool to avoid any intervention. So it means that in case we have such an accident, we have enough water to cool down the residual heat. And when we, let's say, boil all the water, because we are in a situation in which we cannot replace the water, then we will be in such a low residual heat that we will don't need water. So that's with the air cooling would be enough. So it's the most passive system that I know already. You have to do anything because it's in a pool, and the proportion between the water and the heat is such that you don't need to do anything special to deal with this cooling transient. Talking about nuclear spent fuel composition, I think Mate did a great work talking about this let's say, the capabilities of the fast reactor. So I will not talk a lot. Just to say that the most part of the spent fuel is still uranium 238, and we have some, of course, fission products and also some transuranics that we will need to deal with. Well, for a nuclear fuel cycle, we can choose between a closed and an open one. In many countries, we have an open one, like in Spain, in which once the fuel is being spent in the reactor, we just storage it, and that's all. But in other countries, such as France, they reprocess it and do new fuel that it can be used also in the reactors, and they produce different high-level waste in a bidium shape, which is, let's say, much less volume of fuel, spent fuel to store. So there are many designs of fast reactor around. Just to show you the Oculus Aurora, which is under development right now. And the fast breeding properties is just to say that in this kind of reactor we can produce plutonium, which indeed is our fuel, thank you to this neutron absorption of the uranium 238. So it means that if we do it very good, we can have, at the end of the day, we can produce more fuel than the fuel we are consuming. which is very good. So you can imagine that you go to a trip and you put diesel in your car, and when you go to your destiny, you have more diesel than the diesel you put at the beginning. So it goes great. So that's a good thing. So, and also it allow us to have, let's say, um, more understandable and feasible requirements for the repository of the high level waste, because yeah, many of the products can be treated in a fast reactor and getting to more stable way, so it reduces the can be reduced the high level waste management requirements. Okay, another approach for the fuel cycle in advanced way is having a longer fuel cycles. Just to show you, in eVinci we have a 3-year fuel cycle, and we have continuous fuel cycle in, let's say, in a small modular reactor such as the new scale, in which we can replace the fuel during the operation. We have also this approach in the molten salt reactor, in which we have the fuel is within the molten salt of the coolant, and we can just process it within the operation. Okay, some more approaches that can help that has been done for generation 3, and it's undergoing is, for example, the modular construction. In the modular construction approach, which is different to what was done for the generation 2 reactors, we just build the modules of the reactor in one place and start the construction in the other place independently. So we can, let's say, gain a lot of time for on one hand, and on the other hand, we also can have a, let's say, a quicker qualification of the components and the building, because we will do it in a industry, and we will in a factory, and we will move it to the place in which it has to be installed with specific procedures and requirements. Also, with the SMRs, we have the capacity of modularity, but in a different way, in a way in which we can start building one module, operating it, and then with the time we start to do the rest of the modules while the first one are being under operation. So it's a good approach for the investment, because we don't have to put all the investment from the beginning, like in a big reactor. We can split it in different phases, and we can get the best of the first phases once we are paying the last phases. About non-electrical applications, I will not talk a lot, because Matthias did a great job on that. So just to say that with such technologies of high temperature reactors, we can get very high temperatures that can be used for industrial applications, such as oil shale, electricity and steam cogeneration, and also hydrogen generation. So it's a very good approach, and for me is one of the pieces that can be most important. And we have also alternative technologies to bring a gap, let's say, a gap with the next lecture that will talk about fusion. So we can also have these new technologies. So summarizing all the pieces together, at least the most important pieces, if I have to say what the nuclear reactors will be in the future, I think that it's clear that they will have passive systems. It's clear that they will have advanced nuclear fuel cycles. It's clear that they will have modular construction, and hopefully they will have a non-electrical application. So with all these pieces together, I think the best I can say you is build your own reactor. That means I give you the pieces, and you can imagine how it will be. So it's anything from my side. So thank you very much for attending. I hope it's clear, and I'm waiting for your questions.
Very clear, Gonzalo. Thank you very much. And yes, there are some questions already in the chat, both referring to the cooling system. So the first one is from Tobias. And he's asking, are there similar passive cooling systems for the spent fuel pool or only for the reactor core?
Is it very basically for the spent fuel pool? Yes. In some designs, they have these technologies in which they have like a tank that can cool the reactor and the spent fuel if needed, or a passive heat exchanger inside the tank. So they can have these designs.
And then there is Marian asking, could the new scale design passive cooling be applicable for higher capacity reactors?
I think so. Some things yes, and some things not so clear. Some things like this passive natural circulation system are being applied, for example, to the simplified boiling water reactor, in which we don't have these coolant pumps in the primary circuit. So yes. Although, like let's say, this putting in a pool and calculating the heat flux versus the capacity of the pool for a very big reactor, I doubt it. I think is really related with I mean, the pool can be so big that makes no sense from the maintenance point of view to do it. So that's the thing.
Okay, so if there are any other questions, or we can once more time thank you, Gonzalo, for your presentation, and then move to the next one about nuclear fusion. As said before, with Gergo Pokol. Gergo is already here with us. Hello, Gergo.
Hello, and well, I would like to just thank Gonzalo for already mentioning my topic. So I will just try to share my slides now.
Yes, please.
Okay, it should be okay now.
Okay, perfect.
Well, I will talk about the application of nuclear fusion for energy production. Where do we stand now? What are the basic principles and which direction we are going? And the first slide that I show you is something that probably you've seen already. I mean, some kind of it. It's just the energy, the specific energy of the nucleus. I mean, the binding energy divided by atomic mass, plotted as a function of atomic mass of different nuclei. And well, it's a usual figure, and probably all of you already know that the most stable isotope is this iron isotope. And if we approach this from either the direction of heavier elements or lighter elements, we can produce energy. And the only tweaking with this figure is that the x-axis now is on a logarithmic scale. So this is for us to be able to appreciate this huge potential energy gain that we have for the lighter isotopes here. And well, most of your talks were about fission and all these heavy elements falling apart to smaller isotopes. But today I will talk about how to produce energy from fusing lighter elements to slightly heavier elements. And you can see in the beginning of this curve that it has some zigzags in here. For example, we have helium-4. We see that helium-4 is an exceptionally well-binded, very stable isotope. And well, the reason for it that it has just 2 protons, 2 neutrons, and if those just are located in the nucleus with opposing spins, it's a really stable element, nice symmetric one. And if we want to produce energy by fusing lighter elements to heavier elements, our first aim could be helium-4. And if we would like to fuse something to produce helium-4, there are just a number of other isotopes here which we can aim for as a starting element or a starting isotope. Okay, so well, actually, the mark for deuterium and tritium is a bit unorthodox. Sorry for it. I mean, both deuterium and tritium are isotopes of hydrogen. So traditionally, we usually write just H here, but in fusion, we talk so much about deuterium and tritium that we usually mark them with D and T. Okay, so sorry for that. It's kind of fusion specific. Okay, so we have 3 hydrogen isotopes here, and just 1 helium-3 helium isotope. Okay, and we can try to see how to manipulate these, how to fuse these to produce helium-4 at the end. Before going to detail about what we are doing on Earth, I will just give you our main motivation. And probably you know already that we actually have a fusion reactor working quite well and producing lots of energy for us, and that's called the sun. And if we just see how the sun does its fusion, we can recognize that in the beginning it only has hydrogen 1, the basic hydrogen as the starting isotope, and it consists only of a single proton. So it's the simplest nucleus that you can imagine. And at the end, a chain of reactions produces helium-4. And in helium-4, you have 2 protons. Okay, there's no problem with that, but you also have 2 neutrons. And you can recognize that there must be some kind of trick played around here, because we start from only protons and we produce an isotope with also having neutrons. And the trick is here in this very first step, where 2 protons collide, and at the same time, one of the protons just emits a positron. So if it emits a positron, it loses its charge, so it becomes a neutron. The thing is that you cannot just emit a positron because it has a negative lepton charge. So you also have to emit some kind of very light particle having opposing lepton charge without any electric charge, and that's called an electron neutrino. Okay, so this is some kind of peculiar process happening here. And well, first, in order for it to work at all, you need quite high temperatures, and you need these high temperatures so that the collision energy of these protons is high enough so that they can get close enough together despite having this electric repelling force between them, because they are both positively charged. They have to get close together so that the nuclear forces start to act, and they realize that okay, it would be better to stay together and become deuterium. So in the sun, we have quite high temperatures. Of course, I'm talking about the core where this takes place, and it's about 16 million degrees of Celsius. And second, we have to note about this reaction that it's kind of slowish. So actually, it takes for the sun to burn all its fuel about 10 billion years. So and actually, it's kind of nice because it gave us enough time to evolve and to be beings that can think about what the sun does. But still, if we want to burn something on Earth, usually we would like to do it a bit more rapidly. And for this reason, we are not aiming exactly for the same fusion reaction as the sun does, but we are aiming to fuse isotopes that already have neutrons in it. Okay, and so we ruled out hydrogen 1, but still we have 3 different isotopes here. We have deuterium, tritium, and helium-3. And all of these have very nice fusion reactions. Actually, there are 2 that produces helium-4 as an end product, and these are the reactions which produce most of the energy. But actually, it's not really the decisive factor in which reaction we would try first. Decisive factor is plotted here. It's all about the likelihood of the reaction as a function of collision energy. And you can call it a cross-section of the reaction as well. And I have to note that this is on a log-log scale, okay? So the peak here for deuterium-tritium reaction is not a bit higher than the other peak for deuterium helium-3, but it's almost a magnitude, an order of magnitude higher, so almost a 10-fold factor in it. And what's also important is that this peak is at the lowest collision energy. And if we would like to produce these high collision energies, it does matter, we will see. Okay, so that's the sole reason why we are aiming for producing deuterium-tritium fusion as a first feat in today's machines. And what do we know about deuterium and tritium? I mean, deuterium, that's still a stable isotope, and actually every 6,000 hydrogen atom in seawater is deuterium. So you can produce heavy water from it. It's not very expensive. So we have no problem with deuterium. We have a bit of a problem with tritium. And the problem with tritium is that 2 neutrons are just a bit too much for a single proton. So it's radioactive. It decays with beta decay to helium-3, and the half-life is about 12.5 years, which is not terribly wrong. I mean, there are shorter half-lives. So if we produce some tritium, we can actually store it for a while. Yet on the time scale of nature, it's very short. Okay, so there is not much naturally occurring tritium on Earth. It's about the whole supply on Earth of natural tritium is about 100 kilograms or so. And actually, this is nuclear energy that we are dealing with. So a gigawatt power plant would consume about 0.5 kilogram of tritium a day. So it produces immense amount of energy from very little amount of tritium. Yet still, I mean, 100 kilograms is actually, yes, it's just too small. So we need to produce tritium somehow. And actually we are kind of lucky because we have lithium, and lithium is just a bit heavier than helium-4. And actually the binding energy, the specific binding energy of lithium is much lower. So if lithium-6 gets a thermal neutron, it just likes to fall apart to helium-4 and tritium. And actually, it's also exotherm, so there is even a few mega electron volts of energy produced. And also there's another reaction of lithium-7, which now needs fast neutrons. It's an endothermic reaction. It needs energy input as well. And it falls apart to helium-4, tritium, and the slower neutron. And by using these reactions, we can actually produce tritium from lithium, making use of the neutron here that was produced in the deuterium-tritium fusion reaction. Okay, so that's kind of what we are aiming for. We have a chamber where deuterium and tritium fuses, it produces helium-4, and also it produces a neutron. And the neutron is, I mean, it's neutral, so it doesn't really like to interact with all these charged particles here. It will just fly through this substance and into the solid wall of the machine, where we have this blanket full of lithium, and there just it produces tritium and helium-4 from the lithium. Okay, and we circulate the tritium back, and in the end, the fuel we need is deuterium and lithium, and we have plenty of those. I mean, definitely enough for a few tens of thousands of years. And what I personally really like about this concept is that in both reactions that are inevitably needed for producing fusion energy, here and here, the end product that is not used up in closed circles and whatever is helium-4. And I mean, we produced helium-4 because it's really strongly bound, and it means that it's stable. There's no way for it to be radioactive. So instead of the many different radioactive fission products that fission produces, this produces helium-4. And I mean, all of you have seen already helium-4. It's put in balloons and kids play with it, so it's completely harmless. Most of the energy is actually carried by the neutron, and by slowing down, it heats up the blanket, and we can use the heat from the blanket to produce energy. Okay, it doesn't mean that we don't need to worry at all about radiation. I mean, tritium is radioactive. We should be careful about it. And also, whenever we have highly energetic neutrons, it will try to transform anything, not just lithium, into other isotopes. So it can activate the structural materials around it. So we should be careful about what we put there, but still we can avoid very serious activation and producing lots of nuclear waste. Okay, what's the easiest way to produce fusion? Is just produce some deuterium ions, accelerate them. You can, I mean, the collision energies that we need is clearly accessible by some linear accelerator. You just put there 20,000 volts on the grid, and then it just keeps accelerating. And you can produce a target full of tritium, and when the deuterium beam hits it, there will definitely be fusion. The thing is that, however, that, okay, there will be fusion, so it's great for producing, for example, fusion neutrons. But most of the times, and I mean by most, I mean like 100,000 to 1 ratio, so really most of the times, what will happen is that the deuterium that you accelerated will be just colliding with the tritium without doing any fusion reactions, just distributing its energy. And that's why this kind of simple assembly cannot be used to produce net energy for power plant or so. What we really need is to have some thermalized substance full of tritium and lithium, where the temperature is high enough so that the average collision energy is enough to produce fusion. And this is where the thing becomes exciting, because the temperatures that we need are in the order of few 100 million degrees of Celsius. So about 10 times higher than in the core of the sun. That's what we need to handle. And we need to learn what kind of material we have there. And in these high energies, the collisions really rip off the electrons from the ions, so that we have a mixture of free electrons and ions. And that's what we call plasma. And that's where plasma physics comes into the fusion energy production. And there are some very peculiar properties of the plasma. I won't go into details here, but it's very nice thing that, for example, if you put a charge into a plasma, opposite charge will come a little bit closer to it, and the same charge particles will be repelled just a little bit. And the end will be that from a distance, you will stop seeing the charge. So we will just see that it's some kind of neutral fluid. So the plasma actually looks like a neutral fluid on a macroscopic scale, but on a microscopic scale, it still consists of two charged particles. And the scale on which this happens, the change between the microscopic and macroscopic picture, is called the Debye length. And the usual definition of the plasma is that it's quasi-neutral, so the Debye length is small if we compare it to the size of the machine. It's collective, so many particles interact at the same time. And by many, I mean really many, and 10 to the 8ths and stuff like that. And it also has a fourth criterion to feature plasma oscillation. It means that the dynamics, the whole movement of the plasma, is determined by the charge particles. But if we would like to characterize the functioning of the machine from the point of view of producing energy, we usually stick to this energy multiplication factor Q. And it's the fusion power divided by the external heating power put into the plasma. And these are the record discharges. I mean, this is how far we could get yet. And you see that it's below 1. It means that we are not there yet. We could produce fusion energy, but we needed more heat into the plasma from external sources to produce fusion. And that's, of course, not what we would like to reach. In fact, we could even aim for Q equals infinity. And it's very nice. It also originates in the fusion reaction that we are using, that in DT fusion, an alpha particle is produced. I mean, alpha particle is just the hydrogen 4 ion. And about 1/5 of the energy of the reaction is put into this particle. The 4/5 are carried by the neutron. And this alpha particle is a charged particle. It really likes to interact with the deuterium and tritium ions in the plasma, so it can divide, it can distribute its energy and heat the plasma. And if we plot the heating power as a function of temperature, it will have a definite peak here. And the reason is just in the cross-section of the deuterium and tritium cross-section. If you remember, the cross-section already had the same peak. So this gives us a chance to run a reactor in a so-called ignited state with Q equals infinity in a stable burning plasma operation mode, where if the temperature increases for some reason, the losses will dominate and the plasma will cool down. I mean, this is just really a stable operation mode. And this is our dream, that we ignite the plasma and then just sit back, relax, and lots of energy is being produced. Okay, but it's not that easy. In order for it to work, you need high temperatures. Okay, here I measure temperatures in kiloelectron volts. That's also a plasma physicist way. But if you translate it to temperature, really Celsius, it's about 300 million degrees Celsius. And also there's a criteria for the product of density times the energy confinement time. This describes how well you can insulate your plasma. And there's a minimum for that, for ignition. And there are two ways to achieve this. One is inertial confinement fusion, which actually kind of works already, because H-bomb works like this, that the plasma expands freely after ignition. That's what you call explosion in other terms. And so energy confinement time is quite low. So you need high densities to achieve this. And well, you compress the fuel with an atomic bomb. So I mean, you can achieve this. But it's really hard to do in small scale, so that the city around the power plants survives. So there is some research in this direction, but I really like the concept of rather the magnetic confinement fusion, where we aim for a steady state operation. We deal with very low densities. It's a vacuum system, basically. But we try to really insulate the plasma from the surroundings and try to increase the energy confinement time. And what gives us hope is the interaction of magnetic field with these charged particles. I mean, this is just the equation of motion without any collisions, just free motion of a charged particle in a magnetic field. And you can see that the force governing the motion is the Lorentz force. And it's a very nice force. It's perpendicular to both the velocity of the particle and the magnetic field. So what it does, it directs the particle onto spherical motion, or if it has a component along the magnetic field line, into this spiral motion around the magnetic field line. Okay, and here we have the cyclotron frequency, the Larmor radius to characterize it. That's not that important, but you have these particles circling around magnetic field lines, and that's how we can solve the problem of magnetic confinement. I mean, these particles cannot really move across magnetic field, perpendicular to the magnetic field. Well, at first glance, at least. If the magnetic field is slightly inhomogeneous, or there are added magnetic fields, actually they can slowly move across magnetic field. But at the first glance, if the magnetic field lines do not leave the device itself, and I mean, in a toroidal geometry you can do it, then your particles will just go around and around. The problem is that these drifts will slowly move the plasma out of the machine. I won't go into real details here, but what you need at the end is some kind of helically wound magnetic field structure. And there are two ways to produce it. One is a tokamak. It's a Soviet invention from the 60s. It's toroidalne kamera s magnetnými katyushkami. Well, at least as I pronounce it as a Hungarian. And the other one is a stellarator. That's an American invention from the 50s. And both have these helically wound magnetic field lines. This is the solid line here. It winds around in the toroidal magnetic geometry. And they just produce the magnetic field differently. Okay, I won't go into details here, but The thing is that we can produce a magnetic field which confines the plasma. Yet, if we have a few collisions, they can introduce some radial transport, because imagine that the particles are circling the magnetic field line. Yet, if they collide with each other, I mean, by definition, it changes their velocity. They are just shifted to other different orbits, so it's actually introduces a radial transport. But it happened that people found out in experiments that this is not the main transport mechanism. The main transport mechanism is it's called anomalous transport, but actually it's really not found. Come on, it worked just a minute ago. Okay, so there's a turbulent flow in the plasma. I mean, everyone can imagine turbulent flow. Plasma maybe, but you've seen it in bridges and rivers and stuff like that. So turbulence is a kind of a hard topic. And there are advanced ways of confining plasma. And one is H mode, which is very nice because we have this transport barrier at the edge where the turbulent transport is mostly kind of switched off. The problem here is that the gradient can become too steep. And if it's too steep, okay, it works. It produces edge localized modes. These are large scale modes that really modify the plasma there. And this video views the edge of such a tokamak machine. And now you can see that we are in H mode, so the edge is really calm, but from time to time we have these huge transients. And in industrial scale, we don't like transients. So we need to deal with that. Okay, well, I really didn't have time to go into the beauties of plasma physics, but I would like to show you where we stand now. This is the jet tokamak. Today's largest tokamak is joint European torus. This is the Hungarian part of the machine. I just want to point out. Yes, something about that. Okay, but whenever this guy is not in there, we can look in that, and we see the invisible light, the edge of the plasma, where it's cold enough to emit light, invisible. And now we steer the plasma in operation mode where it interacts mostly with the diverter. Now we heated it up. Fusion is going on. It had some flashes, so it was not very stable, but still fusion was going on okay. And it just ended. I mean, that's kind of the record discharge that we have here. It's just a few seconds. It produced 16 megawatts of fusion power. That's quite high. I mean, it's in the industrial scale. Yet it needed 25 megawatts of heating power to achieve it. So we are not producing net energy yet. But still, that's what jet can do. And the next machine, ITER, will do way better. The aim is to produce 500 megawatts of fusion power with energy multiplication factor of 10, which means that only 50 megawatts of fusion power will be needed. And also for sufficiently high amount of time, I mean, not just 2 seconds, but for 500, that's really kind of measurable already. And after ITER, that will still be a plasma physics experiment. It will not produce any electricity to grid. We can think about designing a machine that's called demo reactor that will produce energy for grid. Okay, and we have the Hungarian, the European fusion roadmap that's detailing all these steps necessary. And now we are kind of here. We started executing the roadmap already about actually 7 years ago, and and now we are doing this this research that's necessary. In the end, just after, sometimes in the 50s, to have a fusion power plant that produces at least a few hundred megawatts of electricity to grid. After that, what comes, it's kind of unknown, but I would like to show you an optimistic scenario where we have solved all the technical difficulties of fusion, and it becomes the greatest investment ever to produce fusion power plants, so that it can really take off around the end of the century. But before that, we need some kind of alternative way of producing carbon neutral electricity. And this scenario is not just optimistic from the fusion point of view, but this is also kind of optimistic from the fission point of view, because according to this, fission could take off and produce most of the carbon-free energy that will be needed at the end, till the end of the century. Okay, this is not a prediction, but it's some kind of optimistic scenario that I personally really like. And with that, I would like to end my talk. And after the coffee break, I think that we will have some short video, and after that, I can answer all your questions that you have about fusion energy. Thank you.
Okay, thank you, Gregor. So let's do like that, as you said. Let's keep all the questions arriving. A lot of questions about this very interesting topic. So we can answer all these questions, I think, after the laboratory. So the experiment video you will play later. So I would say to have a 15-minute break right now till 15:55. So then we will be ready to start with the fusion experiment video, and then all your question will find an answer thanks to Gergo. So see you after the coffee break. Okay, here we are back for the laboratory. So, Gergo, please, if you can share your video, we can start.
Okay. So actually, I think this is the best way to do it. And I shall also share sound. Okay. And let's play it. I mean, this is my favorite device, but I'm not very good at producing videos, but we'll see. We'll see.
Hello, I'm Gergő Pokol from Budapest University of Technology and Economics, and today I will show you an experiment that has little to do with fusion, yet it's a very basic experiment of plasma physics. It's a glow discharge tube, and in fact this was one of the first experiments in which we could produce sustained plasma discharges, and that's where originally the term plasma was found for this kind of ionized substance. A glow discharge is a low pressure discharge, so we will need a vacuum system, and our vacuum chamber is this tube made of glass. Glass is very good for vacuum systems, and it is connected to a vacuum pump, and our vacuum pump is a membrane type vacuum pump that is very good to produce such kind of vacuum that is needed here. It's not a very strong vacuum pump, yet still it's just sufficient. The next thing we will need is a high voltage power supply, a DC power supply. This is the one. It is a nice symmetric power supply. It can provide a positive 1 kilovolt and negative 1 kilovolt, both at the same time with respect to the grounding. First we connect the anode electrode to the positive output. Electrons will be accelerated in this direction, and we also have another electrode that is called the cathode, and we connect the cathode to the negative output of the power supply. It is very important that while we are making these connections, the power supply should be visibly disconnected from the mains, so that there's no risk of electric shocks. The final step is to ground all metallic parts, for example the inlet valve. Having set up everything, after the final checks that everything is okay, we can plug in the power supply, and after we can switch it on. The power supply can measure both the voltages. Now it's measuring the voltage, and we can ramp up the voltage, and also it can measure the current in milliamperes, and it can also control the current flowing through the power supply. So we can ramp up both these. And then the discharge tube ignites, so plasma is produced. We can increase the distance between the electrodes. And then we have some plasma. We can increase the light coming out of the plasma by increasing the current flowing through it. The reddish color light, it is called the plasma. And also there is some violet colored light around the cathode that is called the cathode light. If we switch off the lights in the room, we can have a way better picture of what's going on. And having set it up, everything, we can start playing with our plasma. This plasma tube is designed so that it's safe for the public to play with it, even for children. And in this special case, it's Urs, my PhD student, who helps me with this demonstration. And if we look more carefully into the tube, this is what we see. This is the anode glowing in reddish color, and around it the gas itself, that is just rarefied ordinary air, is glowing also in reddish color. And we can tune the machine by letting in some more air. And when we think that our plasma is ready, we can start to demonstrate how the plasma that is composed of charged particles interacts with magnetic field. And this is our purpose of having this machine, that we can demonstrate how we can control the plasma position without ever touching it. So here we can clearly move around the plasma and also change its properties, produce these stripes, and so just by letting the magnetic field interact it. We don't have to touch it with anything, just let the magnetic field do the job. And that's exactly what's happening in a tokamak and a stellarator as well, where we don't touch the plasma itself, we just confine it with magnetic fields. And this is now a very interesting thing. If we increase the pressure further, we can produce these stripes even without magnetic field. And if we then decrease the current going through the plasma, we can increase the number of stripes, and we can extend this stripy area even into the area around the cathode, where usually we have this purplish cathode glow. That's a very nice effect, and it's interesting that these kind of discharge tubes have been around for a century or so, yet exactly simulating how and when these stripes occur and exactly how they look is still kind of a challenge. And there are people doing research still in this area. Now I increase the current again so that the stripes mostly disappeared. And we will let in some more gas now so that disappear completely. And we can also focus on the cathode glow. The cathode glow was quite large, and even now the area around the electrode where it glows is still very large. It almost fills the whole vacuum tube. And probably this is the nicest mode of operation for the machine to demonstrate the properties of plasmas. And this is very peculiar, that the plasma is something that's neutral on a macroscopical scale, yet it consists of charged particles. And that's how it can interact with the magnetic field. And that is what we can clearly demonstrate here. And it's just a pity that it's not yourselves doing this, playing around with the magnets. And now we will see what happens when we input more gas. We increase the pressure in the discharge tube. You can realize that the negative glow area decreases, really contracts onto the electrode. And this is because the mean free path of charged particles in such a higher pressure gas is way, way lower than in a low pressure gas. And if we increase the pressure more, we will see that the negative glow area contracts onto the front of the electrode. At the back we have no discharge anymore. And that's kind of the starting phases of the end of the discharge, because when we increase the pressure even to higher degree, we will lose our discharge. And now I will show you what happens when you finished playing with the plasma. You just steer down the voltage, switch off power supply, switch off everything, basically the vacuum pump, let in air into the vacuum tube. And then you can, when you see the plug of the power supply on the top of it, you can safely start to disassemble the high voltage plugs and stuff. After disassembling the high voltage part, we can disassemble the vacuum system, and we are done.
Thank you, Gergo, for this very interesting video. And so we are collecting more questions. I will say to start immediately replying some of them. So starting from your previous presentation, there was one of the first questions from Marian, asking if tritium supply needs to be pure or it can be extracted from traditional nuclear power plants by fission.
That question is really on point, and thank you, because it gives me a chance to tell you that actually this tritium breeding technology that I've described to you, just vaguely, it's not something that's well established yet. So we actually never tried this technology in a reactor, in a fusion reactor. And the first reactor in which we will be able to try these technologies and experiment with it will be ITER. Okay, and even with ITER, it will be only in the DT phase. So probably the first results on the actual workings of tritium breeding blankets technology will come just at the end of the 30s. So still some few years from now. And the tritium that we need for our experiments, and also the tritium ITER needs for experiments, comes from CANDU reactors that are heavy water cooled and heavy water moderated reactors. Most CANDUs are in Canada and in Romania. And I mean, as they are heavy water moderated, they produce significant amount of tritium just by neutrons interacting with deuterium. And they sell their tritium to fusion researchers. So your question was great. The tritium, that's actually, it's a burden for fission power plants. It's a byproduct. That's actually what we need for fusion. On the other hand, the amount of tritium produced in power plants is quite small. So on the long run, we definitely have to produce our own tritium with a tritium breeding blanket. So the demo reactor or anything that comes after ITER will have to produce its own tritium, because ITER will burn most of the tritium available today from CANDU reactors.
Thank you, Giorgio. And then again from Marian, what is the average quantity of electron volts produced from the fusion of DT compared to the uranium-235 fission, which is around 200 megaelectron volts?
Okay, so in a single DT fusion reaction, just above 17 megaelectron volts is produced. So it's one order of magnitude less than in one fission reaction. Yet, as the fuel is much lighter, if we take the specific energy density, that's the energy density divided by mass, then fusion fusion energy is more. It doesn't really matter, however. I mean, it's kind of the same order of magnitude. You can produce lots of energy from it.
Then Tobias asking, how would you couple the energy from the fusion core to a turbine?
Okay, so actually, the simplest answer is we don't couple it. So in today's machines, which are plasma physics experiments, we don't do it at all. In ITER, we will not do it either, because ITER will still be an experiment, and okay, it will produce some positive energy balance from time to time, but it still doesn't justify building huge steam generators and turbines and whatever. So the traditional way of thinking about it is just using pressurized water cooling in the blanket, and then this is your primary loop. And with this pressurized hot water, you can produce steam in steam generators and drive steam turbines. I mean, like in a pressurized water fission reactor. Of course, on the longer run, we could imagine using helium at higher temperatures, and I mean, all kinds of ways to cool a reactor in a fission reactor. It's also applicable to fusion. You can use molten metals and whatever, but fusion is already quite ambitious in itself. So probably for the first time we will use a more traditional way of cooling the reactor, and that will be with water, because water is just insanely good coolant.
And the next question from Milica: what are the main safety concerns in fusion reactor?
That's a very good question. And I mean, I would like to start by ruling out some traditional risk factors in fission. I mean, for example, the problem at Chernobyl was with the chain reaction. Fusion doesn't have chain reaction. I mean, it means that the product of the nuclear reaction doesn't generate any more nuclear reactions. So we can rule out Chernobyl type incidents. In Fukushima, the problem was with remnant heat. So the reactor shut down, there was no problem with that. The problem was that still a lot of heat was generated by the decaying of the radioactive fission products. And that's why after shutting down the chain reaction, the fission reactors still need lots of cooling. And in a fusion reactor, we don't have fission products. What we have are some activated structural materials. So we should be very careful about what we use for structural materials, so that the activation is not very serious. And then there are calculations showing that even if we lose all our heat, all our cooling, the structural materials will not melt due to remnant heat. So we can rule out Fukushima type problems. And actually that's with this we ruled out most of the more severe accident types for nuclear reactors. But of course, it doesn't mean that we have no risks. And I consider tritium the most serious risk factor, not just because it's radioactive, but because it's hydrogen. And if you ask any chemist, they don't like working with hydrogen. Hydrogen tends to accumulate at higher areas of the room, concentrate there, and then explode. So it's a thing that hydrogen does. So chemically, we don't like hydrogen. So you should really take care how you store your tritium. It's considered to be stored as solved in some kind of metallic material. As hydrogen is so small, hydrogen molecule, it fits in between the metallic crystalline structure. So you can actually store it in palladium or some kind of heavier metal. And but this technology is something that should definitely be worked on. I mean, these are there are kilograms of radioactive tritium considered here in this tritium loop, and care must be taken to avoid any incidents there. Regarding the plasma, I mean, well, it's kind of scary that it's 100 or a few hundred million degrees high, but the whole amount that's in the reactor is measured in grams. So it's basically a vacuum system with some small amount of plasma. If the plasma hits the wall somewhere, it will melt the surface of the tungsten that's on the wall material usually, but it will not produce any major incident.
Okay, thank you. And then we have two more questions coming after the video we saw. And one is about obviously the experiment you show, and are there any acoustic effects of this process? And the second question is related to the stripes we saw with the plasma. Is this a resonant phenomena, or what is a short explanation for that stripes?
Okay, so for the first question, actually, I don't know, because there is definitely acoustic effects of the vacuum pump. So a vacuum system is usually a noisy thing to have around. There are mechanical pumping happening. So this membrane pump also works with the membrane moving, and that's what you can hear. Actually, I haven't put my ears onto the tube to hear if plasma is producing some audible effects, and I think that usually it doesn't. What people like to listen at bigger machines is actually not the pure sound of the plasma, but the electromagnetic effect. So if you just put a small coil at the plasma or near the plasma, then the current flowing in the plasma will induce a magnetic field in the coil. And if the plasma moves around, this field, magnetic field, will change, and the changing of magnetic field induces an electric field that drives a current in the coil. So you can actually translate the movement of the plasma into sound signal. And in many of the control rooms of tokamaks, they amplify this sound signal, and operators can hear how their plasma performs. A famous example is that if you hear a sound, a whistle with decreasing frequency, like well, I probably won't be able to reproduce, but something like that, then you're in trouble, because it means that there's a mode in your plasma that's not symmetric anymore, and you hear that sound because this asymmetric structure revolves around in the plasma, and when the frequency decreases, it means that the plasma rotation is slowed down by this structure, by this asymmetric structure interacting with the material around the plasma. And when it stops, most probably its amplitude will grow and you will lose confinement altogether. And that's what you call a disruption. If you lose your nice magnetic geometry because of some plasma instability, then suddenly all your plasma just hits the wall. And of course, operators try to avoid it. But if you are pushing for the limits in experimental devices, you inevitably have some disruptions. And we don't like disruptions because they can melt some parts of the machine and stuff like that. For the outside world, it's no risk really. For operators and engineers, it's a bit of a headache. So acoustic, it's really nice to hear plasma functioning, and that's why people translate plasma effects to acoustic signals, but plasma itself usually doesn't do it by itself.
Okay, thank you, Professor Pokol, for such an interesting and clear explanation. And now we can move to the next, the final laboratory, the last one. We'll be together. Andras Sige is already here with us. Good afternoon, Andras. And the laboratory will be about the reactor operation, if I'm right. So, Andras, if you are ready and you want to start sharing your presentation.
Okay, good afternoon, everyone. So Gergő bought you some nice orange and violet glow, and I bring some blue glow to the game. We prepared a short introductory or promotional video about our facility, about our reactor. And after that, I will have also a presentation. It's a recorded PPT. And after that, I'm open to questions. Okay. I hope you can see and hear it.
Hungary is a small landlocked country in the heart of Europe. We do not have too much natural resources, so the idea of nuclear power was an early one. The first Hungarian nuclear reactor was built with the technical support of the Soviet Union in the second half of the 1950s. The design documentation was supplied by the USSR, and the work was held by Russian experts on site. This 2 megawatt research reactor first went critical in the spring of 1959, and after 2 reconstructions, still in use today. A research reactor is not optimal for teaching, so to have a place teaching the experts needed for a nuclear power program, visionaries of the time decided to design, build and commission a so-called university reactor. This training reactor was designed in the first half of the 1960s and built in the second half of the same decade on the site of the Technical University of Budapest. First criticality of the new facility was in the summer of 1971. Maximum licensed thermal power was originally 10 kilowatts, but later the core was modified and was uprated to 100 kilowatts. This is a teaching facility designed with students in mind. There are 3 types of student exercises. The first type is using the reactor as a radiation source. A nuclear reactor is a powerful source of thermal and fast neutrons which can be used for experiments. The reactor also produces gamma rays during and after operation. These radiations can be used for experiments like neutron activation analysis, gamma and neutron dosimetry, shielding measurements, determination of delayed neutron precursor parameters, and measurement of the thermal neutron diffusion length in graphite. In the second type of exercises, the reactor is studied as a reactor physical experimental device. Students can perform a criticality experiment to study how to approach the self-sustaining chain reaction in a safe way. Reactivity experts of cadmium and voids can be studied, and the axial neutron flux distribution can be determined by the irradiation of a wire inserted into the core. The third type of student exercise is a class of its own. This is the reactor operation exercise. The reactor is operated by students. They sit in the control room. They push the buttons to start the reactor. and if the student operator makes a mistake, the worst thing that can happen is that the reactor is shut down automatically in less than 500 milliseconds. This reactor was designed with frequent shutdowns in mind. A nuclear power plant usually shuts down once a year for refueling and maintenance, and more than a day is needed for the restart. The training reactor can be shut down and restarted in 20 minutes. Nuclear safety with students around in the middle of the city is very important. This reactor is inherently safe to the usual nuclear accidents needed for the safety analysis report. The excess reactivity is too low to have a prompt critical state, which is also called a runaway chain reaction. Core thermal power is too low to have a meltdown accident, even if all the coolant water is lost. Natural circulation of air in the reactor tank is enough to keep the fuel temperatures in check. Uranium enrichment level and the amount of fissile material in the core is way too low for a nuclear bomb. This is important for safeguards reasons. The facility doesn't have a design life. Frequent fuel replacement is not needed. The current core is as old as the reactor itself. If aging of the equipment is monitored and failed parts are replaced, the reactor can be used indefinitely.
Okay, let me check the chat. Nothing about this video, so the next one is the presentation. Okay, let's talk about reactor operation itself. Going from the inside towards the outside, let's start with our fuel. This reactor is a heterogeneous thermal reactor, which means that there is moderator, which is separated from the fissile material. The fissile material is low-enriched uranium. The enrichment is 10%, so this material is not suitable for a nuclear bomb. Uranium is an oxide form, UO2, which does not conduct heat well, so it's mixed with metallic magnesium. This fuel material is inside hermetically sealed aluminum pipes. It's called cladding. The diameter of the cladding is 10 mm with a wall thickness of 1.5 mm. This is an old design. The wall thickness is much larger than what is in use today. It was designed in the 1950s in the former Soviet Union, and it was over-engineered because knowledge about radiation damage of materials was more limited at the time. Aluminium has good corrosion resistance and practically transparent to neutrons, so it's a good structural material for low-temperature, low-pressure applications like research and training reactors. Our fuel was manufactured before the first moon landing, and we still use the original assemblies. Our fuel has the same age as the building itself. This EK10 type was a standard Russian research reactor fuel. It was designed for a much higher powered research reactor, so that's why it's so safe for this small training reactor. Fuel pins are arranged in a rectangular grid with volume between the fuel for the water, which acts both as coolant and as moderator. The fuel assembly has an outer aluminum shroud to direct the flow and to protect the fuel pins magnetically. This is the core map. In the central region, you see the 24 fuel assemblies, altogether 369 fuel pins. The mass of uranium is about 30 kilograms in the core. 10% of it is the fissile 235 isotope. Fuel region is surrounded by a graphite reflector region, graphite reflector assemblies. The aim is to scatter back neutrons to reduce leakage. This core would be subcritical without the reflector. The chain reaction is regulated by control and safety rods. They contain neutron absorbers like boron and cadmium. The rods move in guide tubes located between fuel assemblies. The two quick-acting safety rods can be inserted in less than 500 milliseconds. Each rod has an electromagnetic clutch. It means if electrical power is cut, the rods are inserted and the reactor is shut down. When starting the reactor, first the safety rods are pulled out, moved to the upper position. This way we always have a safety reserve for quick shutdown. Moving the control rods up automatically inhibited before the safety rods are ready. The reactor goes critical when the two control rods are about 2/3 out of the core. Usually a built-in neutron source is also inserted before startup. This is a plutonium-beryllium source which floods the core with neutrons to have higher neutron flux and more stable neutron flux measurements with better statistics. Without this trick, the natural fluctuation of the neutron flux on very low power could initiate a safety signal and the reactor would be shut down before reaching criticality. The two control rods are called manual and automatic. Both rods are moved manually one after the other by the operator during startup. After the desired power level is reached, the control system is switched to automatic mode, which is like an autopilot or cruise control in a car. In this mode, the automatic rod is moved by a control circuit to keep power level constant. It is used to compensate reactivity effects like temperature changes or neutron absorbing samples inserted into the core. Power level and power level rate of change is measured using neutron detectors around the core. There are 5 neutron detectors. One of them is used for control. The other 4 have safety functions. For safety, different detectors are used on low and high power levels. On low power, in the so-called source range, fission chambers are used. These sensitive detectors are blinded by high neutron flux. That's why you also have 2 less sensitive gamma-compensated ion chambers. Low and high power detectors are doubled for the required redundancy. Safety limits for reactor power is set by the operator. Different limits are needed for different experiments. Rate of change limits are hardwired. If power is increasing too quickly, then we have a scram. You see here the core and its support structure. Fuel and reflector assemblies are in the core basket. Cooling water enters the lower part through these windows or cutouts. Then it takes a turn upwards and flows through the fuel assemblies. The flow is a natural flow based on the density difference between cold and warm water. The reactor can even run on full power for a few minutes without the coolant pump switched on. The pipes you see in the upper part are guide tubes for the control and safety rods, the neutron source, and experimental devices. This whole structure sits at the bottom of the reactor tank. Here you see the reactor tank with the core at the bottom. The upper part is open to the atmosphere. It also enables easy access to the core. Water level is up here, and experimental vertical channels can be accessed through ports here on this shelf, which is 1.5 meters below the water level. This is the shielding when removing irradiated samples through these ports. The tank is inside a concrete structure made of 2 types of concrete. The dark gray part is close to the core. It's the heavy concrete. Its density is increased by mixing barium sulfate to have better gamma shielding properties. Light gray is normal concrete, and here we have 3 dry experimental channels connecting the top of the reactor to the irradiation tunnel. On the other side, there is a channel to remove irradiated fuel, but it has never been used. This is how the core looks like on 10 kilowatt power. You see the blue glow of the Cherenkov light. This is a simplified drawing of our technological system. On the left side, primary and secondary coolant loops can be seen. Water normally enters the reactor tank through the bottom, below the core basket. When cooling is needed, water is taken from a region above the core exit through this pipe. Water is pumped by the primary pump through this heat exchanger. The secondary side of the heat exchanger is not a closed loop. Normal tap water is used to cool the primary water. This tap water leaves the building after a single pass. To be sure that no contamination can leave the building with the secondary water, higher pressure is kept on the secondary side of the heat exchanger. So if there is a leak, contaminated primary water cannot enter the open secondary side. This heat exchanger can also be bypassed when not needed. Then the water enters the heater tank. Moderator can be heated using electrical heaters. This might be needed for reactor physical measurements. Primary water can also be cleaned by pumping through ion exchangers. There are 2 moderator tanks connected to the primary side. These tanks are used to hold spare moderator, which is very clean water. These moderator tanks also have enough free volume to store moderator from the reactor tank. On the right-hand side, you see the wastewater system of the facility. The building has 2 separate wastewater streams. One is for normal wastewater from the kitchen or from the toilets. The other is the special wastewater system, which was built to collect, store, and clean up contaminated water. Water is only released from this side after its radioactivity is measured. Unfortunately, you cannot sit at the controls this year. With the following slides, I'll show you what happens during a typical reactor operation exercise. This graph was generated using the computer logs of a real student exercise. Horizontal axis is time. The left vertical axis is power, and it has a logarithmic scale. This is for the red line. The vertical axis on the right-hand side is linear, and it's for automatic and manual controller position. You see that the control system was switched on sometime before 10 a.m. for testing and then switched off. That's why we are missing power measurement from this period. Then it was switched on again, and student operator started the first startup. Positions of the safety rods are not recorded. You only see when they pulled first the manual rod, blue line, then the automatic rod, green line. Here the operator made a mistake. He set the reactor power trip level incorrectly, and the reactor was shut down. The second try was successful. The time period indicated here is a supercritical power increase. You see that control rod positions were constant, and this straight line on the logarithmic scale means an exponential power increase. Reactor power is doubled every 30 to 40 seconds. By measuring this so-called doubling time, reactivity can be calculated. Lower doubling time means higher reactivity. Our hardwired safety limit for doubling time is 7 seconds. It is defined in a government decree on the safety of nuclear installations in Hungary. In the next time period, the control system was switched to automatic mode. You see constant power here. When power regulation was switched on, the automatic rod, the green, started to move down to put the supercritical reactor to critical state. The first quick part of the rod movement stabilized power, then in the next few minutes, a new equilibrium of delayed neutron precursors was reached. Then we made a small reactor physical experiment. The manual rod was moved down by 10 millimeters. This resulted in an automatic pull of the automatic rod by about 20 millimeters. This shows that the two rods have different reactivity worth. Then later, the manual rod was used to set the automatic rod to 275 millimeters here, which is 25 millimeters below the central position, the midplane. This was done in preparation for the next measurement. Here the control system was switched to manual mode and the automatic rod was moved up by 50 millimeters from here to here. You see this power increase. This is a supercritical state and doubling time can be and was measured and reactivity was calculated. You see that 50 millimeters here means a lot. This is a relatively quick power increase. If you divide the reactivity of these 50 millimeters with the position change, you get the differential rod worth. It's an important number for the reactor operator. After checking out the rod close to its central position, it was moved to the periphery, close to the top of the reactor core. A 50 millimeter movement was tried here also, and you see a much slower, sluggish power increase. Longer doubling time means less reactivity, although the movement was 50 millimeters again. This experiment shows that the rod worth is lower at the top of the core, where neutron flux is lower. Reactor operators don't like this regime. Control is more difficult, and if the rod reaches the top position, control can be lost and power will decrease. This is not a dangerous situation, but it can ruin an experiment. Next item on the agenda was a reactor trip. As I mentioned earlier, the power level where the reactor shuts down automatically can be set by the operator. Here it was shown what happens if power approaches and reaches this limit. First a warning signal goes off, and then if the operator doesn't stop power increase, a scram signal is generated and all the control and safety rods are dropped. This would be a big deal for a nuclear power plant, but for us it's just another day at the office. Then another student sat into the operator's chair and his first try was also unsuccessful. No harm done, let's try again. After the successful second startup, the last part of the exercise was started. Different power levels were set. You see it here, 20 watts, here 1 kilowatt, here 10 kilowatts. you see that the equilibrium positions for the automatic rod were different for the different power levels. Here, here, and here. The later higher power levels resulted in a higher equilibrium position because of the negative temperature feedback of the core. This negative feedback is important for reactor safety. It helps to stabilize reactor power level. Thank you for your attention. I hope that one day you will visit us in person.
So thank you, Andras, for your video. And there is a question from Marian. What is the average time of the startup for the reactor?
It depends on the operator, about 20 minutes. So the neutron source is inserted, the two safeties are pulled out one after the other. Then the two control rods are set to a position where the core is supercritical, and we increase power with a usual doubling time of about 20 to 30 seconds. So in about 20 minutes, we go from a shutdown reactor to 10 watts, where everything is nice and stable, and we don't have we don't have these statistical fluctuations that might shut down the reactor on low power levels. And it's this 10 watts, although the reactor itself is 100 kilowatts, this 10 watts is for many experiments more than enough.
Okay, thank you. Are there any other questions? So if not, thank you again, Andras, for your video, your presentation. And before the coffee break that we introduce the next session, the next event, Xila, do you want to add some information?
Yes. Hello, everybody. I would like to share my screen also for tomorrow for the project presentation. Please look at this slide, and now you can find who will have from the nuclear energy part the presentation tomorrow. I am going to send the whole program during the night. This do not mean anything. It is not on the base of the jury decision. It is only the project presentation. Who cannot see here your name or your project, it doesn't mean anything. I just look at, because a lot of teams make two different presentations, maybe some of them, two for nuclear energy, some of them one for nuclear, another for the medical physics. I just would like to put this program on this way that every team can show their work, but any connection with the jury decision. Okay, I hope that everybody understands this, and I do not receive more letter about the connection between the project presentation and about the awards. No connection. Okay, thank you.
Okay, thank you, Xila, for this information for tomorrow. And now we can have a coffee break till 5 o'clock, and then we will start with the event. I invite you to follow and to stay here with us about the career guidance with several speakers, nuclear professional and experts here for you to answer to your questions. So stay with us, just a short coffee break before 5 o'clock. See you.